So, we continue our discussion on apicidal points. First of all, let me correct a spelling mistake. I wrote apices, actually it will be abscess, not apices, which. So, instead of apicidal point, we call it apsidal points, but the spelling for apogee and perigee was correct. Okay. So, we have derived this relation that R A times V is equal to L by M. We wrote it, I am writing it here because we will be needing it during the calculations we are going to do now. So, I will just want to keep the board empty. Now, there is an alternative proof to this. What we did was we started with a differential equation, we set d theta d u d theta equal to 0 and got this relation. Also, please remember that for an apicidal point, r dot is also equal to 0. So, that means that velocity v, which is r dot r cap plus r theta dot theta cap at an apicidal point, V A becomes R A theta dot theta cap only. So, the magnitude also is simply R A theta dot. Now, so the angular momentum, which is given by m r square theta dot. So, for theta dot we can substitute V A by R A. If we do that at an apicidal point, the expression becomes R A square into V A divided by R A. So, this will again give back the same relation just by substitute, I mean this one will cancel out and rearrangement will give us the same relation. So, we have seen that this is the relation which we can prove it in 2 or 3 different ways, and so the significance of this relation is at a point, extremum point of the orbit where r becomes a minima or maxima, we have velocity component which is totally perpendicular to the direction, I mean to the radial vector that joins that particular point to the origin, and that essentially means that an apicidal point theta is equal to 0 or pi or any other symmetric angle, right. Now, with this background, let us move on to do some problems. So, we start again by problem number 6. Problem number 6 is, here the orbit is given in terms of this equation, which is r to the power n at equal to a to the power n cos n theta. We need to find the law of force and also we have to find the velocity at any point of the orbit, right. So, it is given that r to the power n is equal to a to the power n cos n theta. Do not be scared by this form. I mean, it's not very simple form, I agree, but we will see that it can be reduced, the calculation can be reduced to a very simple form. So, what we do is we write u to the power n, a to the power n cos n theta equal to 1, right, and that means u to the power n is equal to 1 by a to the power n sec n theta, right. So, I mean we will use this later on. Let us take this and take logarithm of this equation. So, it will be n log u plus n log a plus log cos. So, we are taking log in the base of e. So, it is ln actually ln u plus ln a plus ln n theta equal to 0. If we take derivative with respect to theta from of this equation, then we get n by u du d theta, plus the second term will become 0 and this term become minus n sin n theta by cos n theta, which is once again equal to 0. So, this will give you 1 log of cos n theta will give you 1 over cos n theta, derivative of cos n theta will give you minus n sin n theta. So, from this we can write, so you see this n will go off, we can write du d theta is equal to u tan n theta. So, this is one equation which is very useful. Now, we have to compute the second derivative of u. So, we write d2u d theta 2, which will be equal to du d theta tan n theta plus u tan n theta will give you a derivative of sec square n theta, right. Now, if we substitute this whole thing back into the equation, okay, so we just need these two expressions, right, du d theta and d2u d theta 2, and of course, we need to use this form once again, we will see soon. Now, if we substitute this thing into the equation, that d2u d theta 2 plus u is equal to minus m by L square u square f of u, right. Now, if we substitute this, once again we have to substitute du d theta in this equation, which will give you u tan square n theta. Okay. So, this equation left hand side is u tan square n theta plus u n sec square n theta plus u is what? So, we have to substitute u here, right. You have to just keep it like this, minus m by L square u square f of u. Now, if we take, okay, what do we do now? We have to take u common from all these expressions. If we do that, we have 1 here. Okay. Now, okay, you see tan square n theta plus 1 will give you sec square n theta, right, because sec square theta minus tan square theta is equal to 1. So, tan square n theta plus 1, we can get rid of this and we can substitute it with sec square n theta plus n sec square n theta. So, altogether we will have n plus 1 sec square n theta times u. So, this whole thing reduces to u times n plus 1 sec square n theta. Now, let us okay. So, I removed it, sorry. So, once again if we look into the expression for sec n theta from this relation, sec n theta is simply a to the power n u to the power n, okay, a to the power n u to the power n. So, if we substitute it here, we immediately get a to the power 2n u to the power 2n, right. So, sec square n theta, sec n theta is this. So, sec square n theta is a to the power 2n u to the power 2n. If we, so we have u square, sorry, you have u to the power 2n u and u square. So, altogether if we change sides of this, we get L square by m times a to the power 2n n plus 1. This whole thing is a constant, so we do not worry much about it, u to the power 2n plus 3, right. So, that is my final expression, right, 2n plus 3, right. So, if this is my final expression, I can tell you that f of r is proportional to minus 1 by r to the power 2n plus 3. So, this is one answer we have. Now, for the second part, we have to find out the velocity expression. The velocity at any point of the orbit, as we have, okay, so we do not need this anymore, and also the second derivative we do not need anymore, because the first derivative, I mean, for velocity expression we only need the first derivative. Now, v square is L square by m square du d theta whole square plus u square. Please remember that this is not this force is not inverse square force. The force we have got just now, it is not an inverse square force. So, we cannot use the expressions we have derived for either parabola or ellipse. So, what we need to do is, we need to find out expression for velocity by from this relation. So, if we substitute here du d theta whole square, so we have to have, we will get u square inside bracket tan square theta plus 1 tan square n theta plus 1. And once again, just like we did before, we will substitute this with sec square n theta. Now, sec square n theta, from this we did already, but let us do it once again, a to the power n a to the power 2n. So, sec square n theta is u to the power 2n a to the power 2n. So, final expression L square a square, sorry, this is a to the power 2n by n square, not a square, it will be u to the power 2n plus 2, u to the power 2n plus 2. Okay. So, velocity as a function of r is proportional to 1 by r to the power 2n plus 2, right. Okay. So, this is the answer. So, if we start with this orbit, we see that the force law is given by this, and the velocity at any point of the orbit is given by this particular expression, which is proportional to 1 by r to the power 2n plus 2. So, this solves our problem here. Now, let us move to the next problem. Next, we need this, we need this especially for the next problem. What is the description? What is the statement of next problem? Next problem says, a particle moves under the central repulsive force proportional to mk by r cubed and is projected from an apice at a distance a with velocity v. Okay. So, r a equal to a and the velocity is given by capital V. Show that the path is given by r cos p theta equal to a. Okay. So, this is slightly wrong here, I have not given an expression for p here, but okay. So, we will see what is p actually, and the time dependence of the angular displacement may be given by the relation tan p theta equal to v p t by a. Once again, there is a p here and p here. So, we first have to, well, I have not given you what is p, but okay, when we start the problem, we will see that p is actually given by 1 plus k by v square a square v square. Okay. So, we will see that. So, what is the description of the problem? We have a force which is given by F r is equal to, it is a repulsive force. So, it will come with a positive sign. So, m k by r cubed, m k by r cubed, right. Okay. So, if this is the force, then f of u is m k u cubed. Right. Now, if we put it back into the differential equation, d 2 u d theta 2 plus u equal to minus L, once again I keep forgetting this particular expression, m by L square u square f of u. If we do that, we see we have m square k and you have an u cubed here, which will, out of that u square will cancel out and you have this. Now, taking it to this side, we can write the differential equation as, or I will just modify it here, m square k by L square m square k by L square times u equal to 0. Right. It is also given that the particle was projected from an apicidal point, which is at a distance a with a velocity capital V. Now, using this relation, we see that a times v is equal to L by m. So, if we substitute this for, and so, or m square by L square will be 1 by s square v square. So, if we substitute this for m square by L square, this relation becomes k by s square v square, right, which is exactly the expression of P which is given here. So, we replace this, substitute this with P and we write the equation d 2 u d theta 2 plus P of u equal to 0. Now, this is an equation in a very familiar form, and this equation has a solution u equal to a cos p theta plus b sin p theta. A and b are two constants which has to be determined from the initial condition. Now, what are the initial condition? Again, once again, this is the initial condition which is given to us. A is the velocity. So, A is the velocity, A is the distance of initial projection, V is the velocity at time, V is the initial velocity, and as we know, for an apis we can safely consider that it happened at theta equal to 0. So, the initial condition is theta equal to 0, r equal to A, and V is the initial velocity, and at an apis the initial velocity is okay. So, the initial velocity we will just call it V initial, which is equal to V, right. And also recall that in an apis du d theta equal to 0, right. So, we need two initial condition, we essentially have three initial condition. We have at theta equal to 0, r equal to a, du d theta equal to 0, and v initial is given by capital V, right. For the second part of the problem, we will need this one. Right now, we just need at theta equal to 0, du d theta equal to 0, and u equal to 1 over a, that is just from this relation, right. Now, if we put u equal to 1 over a and theta equal to 0, we see that the solution of this equation gives a u equal to 1 by a. So, if you put theta equal to 0, this term goes and this will give you 1, which will give you a equal to 1 over a. Now, if you compute du d theta, which will be a p sin p theta plus b p cos p theta du. So, theta equal to 0. Once again this term will vanish, which will give you b equal to 0. So, first relation gives a equal to 1 over a, second relation gives b equal to 0. So, your solution to this equation is the final solution to this equation becomes, including all this condition, the solution becomes 1 by a cos theta, right. Write it in terms of r and you will see r equal to a sec theta, right. And what is given is the solution, yeah. So, r cos p theta equal to a, it is the same thing essentially. So, whatever I have got here is what is given in the problem. Now, for the velocity part, once again we have to compute the velocity by using this relation that, oh sorry, it is the angular velocity we are looking for, just a minute. So, it is the angular velocity. So, for angular velocity we do not have to, we just have to use this relation, that L is equal to m r square theta dot. Okay. So, theta dot essentially it means m r square d theta dt, right. So, rearranging we get r square d theta is equal to L by m dt integral. L by m has to be replaced by a times v. So, do the substitution by this relation, right, and r has to be replaced by this equation. So, r square will be a square sec square p theta d theta. Right. Now, if you integrate this part, you will get a square tan p theta, there will be a 1 by p coming plus some constant equal to a times v times t, right. Oh, actually we do not need this relation explicitly, because the first relation itself is sufficient at theta equal to 0, and so we assume that the projection has taken place at the initial point. So, at initial point theta was equal to 0 at t equal to 0, right. So, if we put that in this relation, we see we put theta equal to 0, t equal to 0, we get c equal to 0. So, the final relation what we get from here is tan p theta is equal to, so there is one a that will survive, p v t by a, and this is exactly what is given as the solution. Okay. So, we solved problem 6 and problem 8 of this. There is a problem 9 which will be, well, I said that it will not be solved in the class, but we can discuss it briefly later on. Now, but there is one more problem which I want to do in the class, which is the statement of the problem is as follows. Just give me a second, I will find, yeah. Okay. So, we have one more problem to solve in this class, and the problem is there is a particular orbit given and we have to find out the law of force. Now, the orbit, the equation of the orbit is not given. Why I am doing this? There is a reason for it, which you will realize once we solve the problem. There is a significance to it. The problem is, under the influence of central force, please remember it is not in the problem set. So, you have to listen carefully. under the influence of central force, a particle is moving in a circular orbit such that the circle during its path, it passes through the center of force. So, typically for circular orbits, we assume that the center of force is at the middle, right. So, we set our origin in the middle, but this is not the case here. This is the orbit, let us say it is moving in this direction. At some point here, this is the force center. So, your origin is here and this is your axis. So, this much is given and we have to find out the law of force. Now, it is a straightforward problem, we do not need the concept of apsiidal velocities, we do not need the concepts of velocity of the orbit. Why we are doing it? Because it has some other significance to it. Okay. First of all, what is the equation of this orbit? Please recall if the origin is at the center, then the velocity, the equation of a circle is r equal to a, right, if the origin is at the center. But in this case, origin is shifted here. If a is the radius, then this length is 2a, right. So, we can write the equation of the circle as r equal to 2a cos theta for any point. This is my r and this is my theta. What happens is what happens at r equal to 0? At r equal to theta equal to 0, at theta equal to 0, that essentially means this particular point, right. So, this particular point means theta equal to 0 means this particular point, and at this particular point we have r equal to 2a. When we put theta equal to 90 degree, which is, please understand this, closer and closer we are coming to this particular, coming to the orbit, coming to the origin, theta goes on increasing and the limiting value is theta equal to 90 degree. At theta equal to 90 degree, we have r equal to 0. So, this is the equation we are looking for. Now, if this is the equation, then u is equal to 1 by 2a sec theta, right. From here, if we go on with our calculation, we have to calculate the first derivative, du d theta is equal to 1 by 2a sec theta tan theta, d2u d theta 2 is equal to 1 by 2a sec theta tan square theta and sec cube theta, right. Okay. Sec theta tan square theta sec cube theta, right. So, d2u d theta 2 plus u is equal to 1 by 2a sec, just write it in the next line. Okay. So, this term plus this term. Okay. Now, from this, if we add these two terms and if we take sec theta common from the first this term and this term, then we have sec theta into 1 plus tan square theta, right, plus sec cube theta, right. Now, 1 plus tan square theta is once again sec square theta multiplied by this, it will be a sec cube theta adding to this. So, we have a sec cube theta here, there is one more here. So, we will simply have 2 times sec cube theta, which will be sec cube theta by a. Now, what is sec cube theta? From this relation we see sec cube theta is equal to u cubed into 8 a cubed, right. So, put it in here. So, it will be u cubed into 8 a cubed divided by a. Now, this whole thing is equal to minus L by m square u square f of u, right. Yeah, or sorry, once again I think I messed up. It will be m by L square u square y, m by, I always forget this expression. Anyway, so there is an u square here and there is an u cubed here. So, essentially the law of force F of u will be proportional to minus u to the power 5, which tells us that F of r is proportional to minus 1 by r cubed. So, sorry, r to the power 5. Okay, so it is a problem which was not included in my the problem set I have created for the class, but still I wanted to do it because this is a very typical example of a force. Please remember this number, please remember the power. It is inverse r to the power 5th power, which makes the particle go through the force center during its orbit. Now, this result has a very, I mean, this result has some significance in terms of effective potential, which we will be discussing towards the end of this course. Thank you.